exam, by the way, is posted. So in problem 1, part A, the very first part, find the zeros in poles and identify any pole zero cancellation. Now, most people did get this, but what happened with some people was an indicator. And in fact, it was about a quarter of the class. I have never used the command ZPK. ZPK data. Some of you may have heard of it. In fact, I know about a quarter of you have heard of it because that's what you use to give me your answer. So let's go to ZPK data. Because this is the kind of stuff, this is a small point. It was only a point off, or at most 2, but it's a very small point. So what I did is I generated a transfer function. There's a transfer function. It's 10 over s squared, 10 over s plus 2. Right? Okay? Then I did what a third or a quarter of the class did. I did ZTK data. And here's what I got. And what it shows is, of course, we have a pole at 0. Damping is -1. Explain. What does it mean, Mr. MBA? Yeah, you're dressed like an MBA. Remember me when you get to Akash. What is the -1 damping mean? What does a -1 damping ratio mean? It means you've just created energy out of nothing. Because perpetual motion is 0 damping. That means it goes on forever. And nobody's been able to devise a perpetual motion machine in the history of mankind. But MATLAB tells you can actually have negative damping. So all you have to do is give it a little bump and it goes off forever. Negative damping doesn't mean anything. That was a little thing I didn't worry about that. It was this thing that's really bothersome. You have a pole at -2. Now what does it mean if you have a transfer function that's this? What's the impulse response? There's your Laplace table pair, right? Transfer function, impulse response. So this thing has an impulse response that looks like this. All right? Okay? MATLAB tells me in this command that this pole has a damping ratio of 1 and a natural frequency of 2. Okay? Let's create a transfer function that really does have this. So this would be a final exam question in class, no paper. Create an example of a transfer function that has this. Can you do it? The simplest way to begin is not with the poles, it's with your mantra that you have, which is a constant. It doesn't matter. Two times 1 times 2, right? There it is. Where are the poles of this system? -2 and -2. It's a critically damped system. This is a critically damped. You have S1 and S2, -2, both of them, right? What it's telling you is that the system is critically damped. You're on the verge of being overdamped or, more importantly, underdamped. You're on the verge. Right? If any parameters, if any of the variables in here were to change a little bit, you'd have an underdamped system. This thing, what happens if that number changes a little bit? You can never get an underdamped system. Yet it's telling you that you have a natural frequency and you have a critical damping ratio. And that's not true. So no matter what MATLAB tells you, this is ridiculous. Okay? So that was one example of what people ended up doing. They ended up taking MATLAB commands and bringing them to play when I've intentionally avoided ZPK data. The other thing in ZPK data is actually K. What is K? Oh, actually, no. This was actually not ZPK data. The ZPK data was weird. You guys help me on this. I did ZPK data of GP, and this is what I got. What? So I did this. Now, I think some of you that use ZPK data actually get zero pole information out of it. I couldn't get any. Z is a number. Z is just size Z, or size P. P should have two elements in it, right? There's two poles. So I used damp. All right, the damp command, which I also, by the way, have never introduced in a class, but being the creative engineers that you are, you got it. So I have to give you credit if that's, the command you use. Now, in terms of min real, let's go back to the exam. So that's one example that makes me cringe about giving you a third exam as a take-home. Because I don't want to have to deal with you scrounging around for commands that you think might be appropriate and not demonstrating any knowledge, but demonstrating you're really good at hunting for things that might work. So let's go to, that was one problem. This was a major problem amongst probably 70 to 80% of the class. The minus 3 dB bandwidth of the system is the frequency at which you go from static or operable bandwidth down to negative 3 dB. It is not here to here. We've talked about this repeatedly with an accelerometer. I've given you this plot repeatedly. Here's an accelerometer. Accelerometer has a resonance up here. You don't use the accelerometer up here. Okay? If you want to talk about the minus 3 dB bandwidth, you say this is the operable range. We go down 3 dB here, and we go down 3 dB here. So this would be the bandwidth. Purely minus 3 dB. This is the bandwidth definition most controls engineers use, is the minus 3 dB. I'm not a controls engineer. I'm an engineer. And I think it's deceptive. I told you this before. Why is this deceptive? I'm telling you this thing is good from 5 hertz out to 20 kilohertz. I'm trying to sell you something. I'm telling you this is a very wide bandwidth accelerometer. So you think the useful range is 5 hertz out to 20 kilohertz. And you buy the thing. You pay through the nose for this thing because it's a very high bandwidth instrument. What's the issue? It's not good up to 20 kilohertz. It'll kill you at 15 kilohertz because you got this resonance at 16 kilohertz. So the true bandwidth, the plus or minus 3 dB bandwidth, you do this. But you don't do this for your plus or. This is not the operating range. This is a resonance. You very, very rarely want to operate any system at its resonant location. So that was something that, like I said, probably 75% of the class. Now that's a little thing. It's only a couple points. That wasn't the very, very difficult part to grade. Okay? The parts that got difficult to grade included this kind of stuff. Not many, probably 80, 75% of the people in the class got this. But when you leave an S in here at the end, you missed a fundamental concept. Your units are not correct. All right? You don't know what S is. Some people actually put an S squared times S plus 1. Well, this is, some of you are shaking your heads, and I'm saying, I was shaking my head too, and it's a little problem here. I could grade it easily here, and I can put this on a final exam in class with no notes and expect that you should know this. The bigger problems that I have to do with, oh, and by the way, I did actually post my development of this thing, all right, on the website in the lecture section, and I think you might want to look at it because I also posted, this is aero engineering, where this isn't controls, you're talking about zenith estimation, where things are coming over horizon. I put a PDF file because I didn't know much about this, so I searched for zenith. And I got this file, and they were making these approximations that I was shaking my head at and going, no, this does not happen. I know that the angular velocity is not constant. When I see the helicopters and the DNR flying over my cabin to see if anybody's fishing without a license, these guys come in slow, but then when they're overhead, they're fast. And I looked closer at this zenith file, and it said, oh, this is for high altitude. Where basically, wherever you look at this thing, the angles, its angular velocity is the same. So I said, no, I don't want that. I want a low-flying ICBM, all right, or a drone or something. So I derived it to get this, and I actually had to do a minimization because it's a very ugly equation that you get. But now with MATLAB, it was easy to do the minimization. You guys are in a really beautiful situation right now. There's a huge amount of theory that is not being used in engineering. All right? And the reason it's not being used is because you don't know it. This is theory that was done, much of this theory on polynomials and stuff was done in the late 1800s by Gauss and in the early 20th century by Zagel and Grenander. These were polynomial people. And the equations they got were freaking ugly. But they were beautiful at the same time. Why were they ugly? Because nobody could ever program them and solve them. And so they sit there. This is the most elegant stuff around, and it sits there. But now, me, because I know this stuff, I can program this beautiful theory up and actually see the solutions to these things. And I feel bad for you people because you're not exposed to so much wealth of knowledge that was generated before you. It's all about numerical approximations now. We'll just do it by finite element methods, where in fact you've got solutions to these things. You don't need finite elements. You just need to take these solutions and do the actual MATLAB programming to see what they look like. So anyway, it's there. Now, when we get into here, I talked about this last time. Design a lead controller. I had talked about this lead controller. One of the specs is that it has, first of all, as I said last time, I got all manner of forms for the transfer function of your controller. And that made life really painful for me because then I had to program your controller up so that I could use your controller to see if in the remaining parts of the problem, even though you chose the wrong controller, you actually got right results, because I don't want to double penalize people for stuff. But a lead controller has this general form. And some of you went back to the book and used the author's notation, which is fine, except I strongly discourage you from using that notation, which is about T and what he calls beta or alpha, whatever. I prefer to write this way. Why? Why is this preferred to this? If I ask you, what is alpha, and you've had a controls course, you know what you're going to tell me? Oh, it's the zero of the transfer function. All right? And what's beta? Well, beta is the pole. And I'm like, that's so very exciting to me as an engineer. I couldn't be more bored. But if you tell me that this is a controller whose bandwidth basically goes from a small omega to a larger omega, then as an engineer who likes to work with frequency domain, I say, you mean it does this? It's a high-pass filter in a way, or high-pass amplifier. This has physical meaning. All this does is have pole zeros. Now, is Leon? I met one of the 331 students at Tums last night and was told by his friend that I should ask him to dance because he goes to the gym and dances on the pole. He really could. I mean, we've got poles and we've got zeros, but we've got a 331 student who dances on it. So, I mean, it can be interesting stuff, but this is more direct. All right? And again, you know, when you bring this other information in here and you have the author's method of expressing these things, I have to convert my solution to this solution. And it's okay. I didn't take 10 points off for that. I'm just telling you, it makes more work for me. Because I think you're just grabbing a formula and you might not really understand the formula. You're just grabbing a formula from the book that you think will work. This controller, this problem was meant to be extremely simple. You've got a controller that looks like this. Specification 1 says that the controller must cancel the plant pole at -1. What does that mean? The controller has to have a 0 at -1. I was trying to make life really, really easy for you. So now your controller looks like this. Okay? It has to be a unity static gain controller. Was it in this problem what was unity? No, just a lead controller, right? So it's got a K in the front of it. All right? So there's 2 parameters now that this controller have to be found. So what I said here is use the root locus pole placement method for this controller. When you put in more poles and zeros in this thing and you start using root locus, it makes my work an order of magnitude more difficult. Because you're now doing pole zeros, you're adding up angles and making sure angles equal 180, and I didn't want you to go there. I wanted to make life really simple for you because now what happens is that G of S, we have, this is GC. We have GP. So this thing becomes right? Because the S plus 1 upstairs cancels the S plus 1 downstairs. Now do the root locus on this. I actually drew this root locus in class. We went this far in the class. Some people may not have been paying attention or may not have been here, but the problem was intended to be really straightforward. The root locus for this thing looks like this. That's the most fundamentally easy root locus I could ever have you draw, other than just one that goes straight to the left. Now, one of the specs was the time constant of the closed loop system. Any time constant related to a closed loop pole has to be less than 0.2 seconds. Here was a major problem for me. Let beta equal -5. Then 1 over beta is -0.2. So I'm going to choose beta equals 5 because I have my time constant at 0.2. What's the problem with that?
Once you turn the gain up from 0, it's not that.
So when the gain is 0, when k is 0, as in we don't even have a controller, we have nothing. Mm-hmm. When the gain, this is an open loop time constant. It's not a closed loop time constant. And that became very problematic because then when you choose this at -5, the root locus goes like this. But this is the tau line. This is tau equals 0.2. Right? It's 1/5. So what it means is that as soon as you turn the gain up from 0, both of your poles will not satisfy that time constant. Because they're always to the right of that tau line. And of course, that makes for more problems. The final thing that people did is they actually plotted this, but forgot about using the number that puts you there. They forgot the k value. And again, this is the kind of stuff that I would feel very comfortable giving to you in an in-class 2-hour final. All right? And it's easy for me to grade, and it gives me an assessment of whether you understand if you know what you're doing. What it doesn't do is allow you the opportunity to actually sink your teeth into something and learn and apply something. And there's my dilemma. I could go on with this, but the solution is posted. I don't want to continue this. What I want to do now is bring up some of your food for thought. I had one person email me saying that I can see why you might want to do an in-class final, but I feel that I've really learned a lot from these exams, and I think it would demotivate me to have to just go back to the rote learning and memorizing so that I can jump through the hoops on these little things. They are little things, but mind you, if you don't know them, they're huge 40-hour fudge fests for me. They make it a nightmare for me. So this is why I'm considering having an in-class exam. I haven't decided anything yet. So you don't have to change my mind. All you have to do is push me a little into the right half plane so I can have more exciting life. No, I'm kidding. Food for thought. Yes?
Did we send you like digital copies of our code instead of having you type it all in? Like, for our exam?
There is no way I will ever run anybody's code to grade a final again. No. That isn't the point. And the biggest problem I had with stress was when it says solution. Now, in this one it didn't, but let's go to the other, at a point where it did say that, which was this one. Some people put, you know what they put here? The answer. Just the answer. And it's, see my code. And I got really wound up about this over time because to decipher your code is really time consuming for me. When it says see code, the code, and it's, first of all, when it says solution, you need to show work. All right? When it says see my code at 3A or 3B, what that means is that is support for your work. That is not the solution. Especially in this problem, absolutely. This is my solution. I don't need to show you the Bodhi command. I mean, there are pluses. But in this problem, where you're actually designing something and you show me no design procedure, all you show me is your final plot. And I think that plot may be wrong, in which case I'll definitely go to your code. But I got to the point where even if your problem picture and your code was correct, I would go to and check it. Why? is I found a number of papers where the code in the back had nothing to do with the right answer. It's a take-home exam. And that starts to really frustrate me, because I used to think that, you know, if you got the right answer, yeah, and I look in the back and I see there's code for part 2B, yeah, okay. Then I look more closely at the code, and the code is nonsensical, and I go, this is not good, because now I have to take these 20 exams that I've already graded and go back and check them. So I will never grade code again. No, I won't. And this was a real learning experience for me, so thank you all very much for that. Excuse me? Come on, say it.
We're just being sarcastic. We're just trying to help your personal growth.
No, absolutely. You don't think you're helping me? No. Sarcastic? I tell you, you guys are fundamental for my personal growth. And I say that in a complimentary way. I mean it. Sometimes growth is painful. I dealt with this shit. And I've used that term politely. I should have said something polite like nerd. What a shize. But I didn't. No, I do appreciate it, but I don't want to go through it twice. It's like marriage. Oh. For some. So, what do you want to do? We got 3 minutes here. I can leave the room and we can have Cody monitor this and take a poll, and just so you guys don't have to expose your feelings about that dickhead Sherman who sucks, and I don't want to say anything when he's in this room because he's an asshole. Some people feel that way, and I feel bad that you feel that way, not because people don't think I'm an asshole. It's because when you think that way, it generates negative vibes in you, and it makes toxins in your brain. Do you know that? Do you know that hating people and being angry at people generates chemicals in the brain? That's why stress is such a major health hazard. I don't want to be the source of these negative chemicals in your brain. So if you gotta hate me, at least laugh at it. Don't take it serious. What do you want to do? Yeah.
Should we like get rid of the final letter?
And replace it with what? I don't think many people actually, having shown you that histogram, I don't think many people would care to have that happen. Because right now they're not doing as well as I think they would like to do. So there needs to be another opportunity to show me that this was a low blip on the radar, but that in general, remember I told you this in the grading. If I see an exam that's a low blip, but all your other performance is significantly above it, I'm going to tend to ignore that blip. No. I mean, in the core syllabus, I've already said I've given the grading scheme. I have to stand by that or I'm going to get pulled on the carpet. There has to be 3 exams. Each exam is worth 25%. The homework is worth 25%. If I break that protocol, there may be a couple students, rightly so, who go and complain about it, and then I get in deep trouble. So I can't really do that. Yeah.
How about replacing it with like a homework or a project or something?
After just spending 4 years, funny. I like that. Yeah, I've graded projects. Oh my gosh, and it's worse than grading exams.
How about a group project that you grade less?
It doesn't. I give all projects in 573 and in 432. I give projects. Those take more time to grade a project of 4 than it would take to grade 4 exams.
Group exam?
Group? Well, you just had one. We're out of time here, folks. Let's talk about this. Think about it over the weekend. If you want to email me or start a little discussion site, just give me the link so I can see. If you don't, we'll talk on Monday.